I'm Mary Town, and I've been a speech therapist here at Methodist a long time. It's my pleasure to introduce our speaker today. Jeff Snell is the Director of Psychology and Neuropsychology Services at QLI, speaking with us today on the cerebellum, motor regulation, and so much more.
Thank you much. Well, thanks everybody. You might have noticed the title is just a little bit different on this one, and it's because I ended up updating so much stuff in this presentation that I figured I probably better change the title at least a little bit to make it look a little bit different. I presented on this topic here actually just a few years ago, and the reason that we're going over this one again is because there is so much that has changed just within the last couple of years about what we know about the cerebellum, Tara, and what it is responsible for. So just to give you a little bit of information about me, this is my professional home. I work at QLI, although I live in Virginia. I am sliding my way slowly into retirement. So a couple of years ago, moved to Virginia, but I'm still working remotely full time. So Starlink gave me that ability to begin with, but they recently ran fiber optic cable, so we're good to go out in the middle of the woods in the middle of nowhere in Virginia. So a lot of you are probably familiar with QLI. There are some very familiar faces in the room from QLI previously as well. So thank you again for the opportunity to present this topic to you today. What we're going to be talking about here is, again, a quick review, the cerebellum, a tightly packed group of cells at the very back of your brain that really makes up, and estimates will vary depending on the source you look at, but of the approximately 83 billion neurons that a human brain is purported to have within it, somewhere between 60 and 80% of those neurons are located within the cerebellum. So clearly it plays a very important role. Although it's considered as separate from the brain, we also have to remember that it is a part of the brain. So in the same way that we sometimes differentiate organs within the body and we talk about the mind being different from the body, the brain being different from the body, it's all one unit. It all rises and falls together, even more so between the cerebrum and the cerebellum as they are intricately linked. Now, we know a lot more about the cerebral cortex than we do the cerebellum, and we'll talk about within this presentation why that is. Part of it has to do with the ability to differentiate, to map functional abilities to a specific location within the cortex. Most of you know, speech therapists in particular, this region right up in here, Broca's area is very much associated with expressive language. You damage that area on the left side of your brain, and it is likely that you're going to present with some pretty dense aphasia. That is a common finding associated with that. We haven't had the same level of differentiation and regional identification within the cerebellum, and so that's one way in which it has historically been different. Also, with the difficulty of performing the same types of analyses and differentiation on the cerebellum. And we'll talk about why that is as well. Now, as we'll also discuss, the cerebellum operates on different neural principles than the cerebrum as well. So it is organized from a cellular standpoint very differently than what you traditionally think of when you think of the brain, the cerebral cortices. And so it is different in that respect, physically, structurally different, but it is also much more fluid in its operation as a result. Made up of left and right hemispheres, and there's a narrow kind of midline in the middle that is called the vermis. Latin features into this a whole lot, as it does in most medicine, Latin and Greek. And the cerebellum in Latin means little brain. And the vermis, which is that middle section, is the Latin word for worm. It's because that is kind of the shape and look of it. So when they were originally doing those anatomical studies, that's where that name comes from. The folds that are typically used to divide the cerebellum's overall structure into 10 smaller units that are referred to as lobules. They're somewhat difficult to differentiate when you look at what you're seeing right here, actually on the physical structure of the cerebellum itself. in anatomical studies, it is somewhat difficult to find where is the zone. I mean, with the cerebrum, it's a lot more easy. You've got that central sulcus that you can divide the parietal and frontal lobes and other regions. But this is a little bit more difficult. So this graphic here simplifies the labeling of those lobules a little bit that are trickier to see in physical structure. They are each very similar in terms of their structural organization. So each of those lobules has the same architecture within them. They are not differentiated in terms of architecture, only in location. Now, this used to be significantly different consideration for what the cerebellum is responsible for. If you look in just about any medical textbook, even currently published medical textbooks, they will tell you that the cerebellum regulates, mediates, fine-tunes, and automatizes motor functioning. So with repetition, your cerebellum is programmed to repeat motor function and to have a predictive aspect, as we will talk about. Very little is said about cognition and emotion up until the research from the last, I would say, 2 to 5 years, where it's really become much more differentiated. Now, the fact that the cerebellum is involved in things beyond motor function has been known for a very long time, particularly by those that are involved in rehabilitation, because you have someone with an isolated cerebellar lesion who presents with emotional difficulties, with frontal executive dysfunction, with language disruption, with decision-making impairment. So it's been known for a long time, but it's been very hard to map that, and it's been very hard to prove those direct connections. So that's where a lot of the stuff has changed, and why a lot of the references that I have at the end of this talk are based on articles that are either about to come out or have come out within the last couple of years. So if you enjoy learning about the brain, this is an exciting time to be around, because there's all kind of new stuff that we're constantly getting and learning about. The interior structure of the cerebellum looks like a tree. It is called, again, a Latin word, arbor vitae, 2 words, which means tree of life. So this is the bundles of myelinated axons that carry information to and from the distinct lobules of the cerebellum, from the points at which that information either comes in from the body or from the cerebrum, or goes out to the body and to the cerebrum. The white matter is made up of these segregated bundles of axons that service distinct lobules, facilitating communication with the cerebral cortices. Each of these lobules has a very similar cellular organization. In computer terms, it is very much like multiple processors on a chip. So in other words, a problem can be broken down and solved more quickly if it can be distributed to a network of processors. There's a lot of information out there nowadays on artificial intelligence and these AI centers that are being built, which are basically massive distributions of multiple processors, multiple computers, each of which have multiple processors. So it is dividing that information rapidly, running it through a process, coming up with an answer and spitting it out relatively quickly. That is what the cerebellum does, and does very, very well. That distinct area of communication passes through these pathways. Now, the cerebellum reaches full structural growth in somewhere around our 15th to 20th year of life. And as you might expect, with over half of the brain's neurons located in this clump of tissue that makes up less than 10% of the brain's volume, these densely packed cells have very rich interconnections. So you have a lot of cells that are very close together, and as a result, it facilitates the number of connections that exist. Now, usually in a textbook, when you look at a picture of a neuron and the axon that's sending the information out, and then it interfaces by way of synaptic communication with the dendrite of another neuron, that one-to-one relationship. That does exist several places in the body, particularly the spinal column, but within the brain itself, within our cerebral cortices, every neuron interfaces with somewhere between 1,000 and 10,000 neighboring cells. So it is much, much more complicated than can easily be expressed in a simple graphic. Within the cerebellum, that gets jacked up even further. Within the cerebellum, there are particular cellular layers here in which a single cell will interface with somewhere between 100,000 and 200,000 other distinct inputs. So you've got a lot of cells, many of which are very, very small, sending signals to each other very, very quickly through a multitude of parallel processors. These are the different layers here. These densely packed cells have rich interconnections, and the granular layer that you can see there kind of in the middle, the granular layer is what gives rise to the most abundance of neuronal cells. This is where the tiniest of cells, there are more granular cells within your brain than any other type of neuron. That is the layer in which they reside. They work collectively to make refinements based on prediction of prior knowledge and experience. One time when I was presenting this at QLI, I had a practical demonstration. It is so much easier to talk about the cerebellum in terms of motor functioning because you can see the end result. You can see the motor functioning. The process of doing this and doing it accurately is a result of your cerebellum operating like it is supposed to. And to demonstrate that, I had 5 paint cans on a table, and I had a volunteer come up, and I told him, what I want you to do is grab each paint can by the handle and raise it to your eye level and then put it back down on the table. Of course, one of them was empty. And when they reached that one, it went like this. And the reason that it popped above is because from the first 2 or 3 that they had picked up, they had programmed their brain to recognize that stimulus and know exactly how much force to put into the muscles to get it exactly where they wanted it as quickly as they could and put it back down. And when that prediction was wrong, because it weighed much less than they anticipated, then they had to recover from that. They had to bounce it and get it right back to the same place. Now, if you programmed a mechanical device to give that same amount of force to a full paint can and then gave it an empty one, it would throw it to the ceiling because it would not recognize as it was beginning to pick up that something's wrong. This is off. This is much lighter. And it would not react in the same way. So that's what our brain does, and it does it amazingly efficiently. The outer layer that we're talking about here that you see within the molecular layer, you have these fibers that go up into that area, and they're called T cells, and you see the little arrows where it goes up into that layer and then out. And those T cells lie parallel within that layer of tissue and then also interact with the ones in red, the Purkinje cells. So that process at each stage is just very efficient, very fast, and operates, again, the same way in each lobule, regardless of where that information is coming from or going to. So as we move out from the center toward the outer layers of the folds, you come to where the activity within the cerebellar cortex really occurs. Like the brain's cerebral cortex, the outer layers are made up of tightly packed neurons that communicate with each other, and then through projections out, the white matter that then gets bundled within our brain and then goes to wherever it needs to go to transmit that information. Parts of the brain talk to each other, parts of the brain talk to the body. Same thing for the cerebellum. There are 3 distinct layers within the cerebral cortex. The granular layer that I mentioned a minute ago, where all of these very, very tightly packed cells reside. The Purkinje layer, which is a very single cell deep layer that flows along there. And then the molecular layer where all the interface of that information comes from. So within the granular layer, there are tiny granule cells and Golgi cells, and these layers pass information by way of what's called the mossy fibers up into that outer molecular layer. These projections, the mossy fibers, are excitatory in nature. So in other words, they are sending a signal that cumulatively will determine whether or not the Purkinje cell will fire. the Purkinje cell that interfaces with all of those T cells across there. The granule cells have those T-shaped axons that extend up into the molecular layer, and the top there, again, is called a parallel fiber. They're in the outside surface and of the molecular layer, and they communicate across all of the Purkinje cells that lie there. The parallel fibers form hundreds of thousands of synaptic connections within multiple Purkinje cells. Now, this is a Purkinje cell. It is a very densely branched cell that extend into the molecular layer. And that green ball appearing on the left at the bottom, that would be the base. That would be the cell body from which extend those dendritic branches. It looks like a tree or a bush of some sort. And those dendritic branches receive signals from those 100,000 to 200,000 other T cells that they interact with. That is where all that very complex information goes. Now, what is not pictured here is at the bottom of each of those Purkinje cells is an axon. They're like neurons in which they receive information, and then on the basis of how much excitatory information, if it hits that synaptic potential level, if it hits that action potential that causes that cell to fire, what's not pictured is the axon. There is a single axon from each of those Purkinje cells that then form the pathway of information that eventually will make its way out of the cerebellum and go to wherever it needs to go to do what it needs to do. Now, Purkinje cells themselves are inhibitory in nature. So the signal that they send is inhibitory. It makes another cell less likely to fire. I'm pretty simple when it comes to analogies, and so most people are familiar with cars, and if you drive an automatic, you know that there are two pedals, one of them makes it go and one of them makes it stop. The brain operates in the same way. Neurons are kind of ones or zeros, and that one, when it fires, can either be excitatory in nature, it can release a chemical that is excitatory and causes another cell to be likely to fire, more likely to fire, or it can be inhibitory. These are GABAergic cells, and so they send out an inhibitory signal. Now, where it gets really complicated, when people ask me questions about the brain, usually the first thing out of my mouth is, it's complicated, because there's rarely a single answer. It's why depositions, when you're talking about the brain, is really difficult. There's rarely a single answer that is accurate. If you give an accurate answer, it is incomprehensible, to me included. It's really, 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 really complicated. But you have to think that there are multiple, you know what a double negative is, right? A double negative results in a positive. If an inhibitory signal inhibits another inhibitory function, it actually makes it more likely that something is going to happen. I mean, that's one way in which dopamine actually works when it comes to Parkinsonism, is taking the parking brake off so that movement can occur. So all of these pluses and minuses eventually end up with some regulation of cell function. Now, deep within the cerebellum, there are also these cerebellar nuclei, and these are the main centers of communication. That's where information comes in and goes out. Dentate, emboliform, vestigial, and globose are the nuclei there. They receive and send information to and from specific parts of the brain. The cells within these nuclei also receive excitatory and inhibitory signals from other parts of the brain that modulate these outgoing signals from the cerebellum. Blood flow for this area comes from the basilar artery and the vertebral artery. Those are the arteries that are the primary supply. The basilar artery branches into blood supplies via the superior cerebellar artery and then the anterior inferior cerebellar artery. The vertebral artery, on the other hand, sends blood to the posterior and interior aspects of the cerebellar artery. Now, fibers communicating with the cerebellum are grouped to form three structures that are called peduncles. Weird word. The superior, the middle, and the inferior, they connect to the cerebellum by way of the midbrains, the pons, and the medulla. So our midbrain structures are those that communicate with the cerebellum by way of these primary bundles of fibers. The superior peduncle is efferent in nature. It is sending signals out away from the cerebellum. The middle and inferior peduncles are afferent. They are receiving information into the cerebellum from the cerebrum and from the spinal cord. Our cerebellar cortex, our up cerebellar parts of our brain, left and right hemisphere, that information travels down the white matter by way of these peduncles into the deep nuclei of the cerebellum. It is processed and then it passes back out by way of the peduncles. That's the way that information gets to and from, and eventually back up to the cerebral cortex. Now, this is a graphic that kind of illustrates the parallel processing aspects of the cerebellum. This schematic represents the way by which information comes in, processes through the system, and ultimately results in information returned to the source or to the body. That information travels back down the white matter to the deep nuclei and passes out of the cerebellum by way of these large bundles of fibers. Signals within the cerebellum move unidirectionally. So in other words, information comes in by way of this input there, the superior peduncle. Then it gets distributed. These mossy fibers then extend up into that cellular granule layer, and then that goes to the Purkinje cells. And so it's like having multiple processors from a cellular organizational standpoint. Information gets broken down and passed through this very, very rapidly. A lot of information. For those of you that are familiar with computer terms, researchers have worked out that our optic nerves carry around 80 gigabytes of information per second to our occipital lobe. That's a lot. That's a lot of information really, really fast. If you kind of upregulate that to the number of fibers that are contained within the input and output of the cerebellum, then that extrapolates to approximately 3.2 terabytes of information per second that the cerebellum is capable of processing. That is way beyond supercomputing at this point. We're not close to that yet. The cerebellum can process a massive amount of information very quickly because of this parallel process. It breaks calculations up, distributes it to multiple processors, and then sends it out where it needs to go. The cerebellum operates in conjunction with the cerebrum on a feedback loop. The input channel synapses in the pons crosses over to the contralateral side, so that's why the left cerebellum interfaces with the left side of your body and the right side of your brain. That's where that occurs, is within the pons. As we'll discuss shortly, this feedback loop is a constant ongoing conversation between our cerebrum and our cerebellum. It doesn't necessarily involve any motor output at all. If you think about moving your arm in the manner in which you would to hit a tennis serve, your brain goes through all of those processes from the thought construct, but prevents the motor output unless you intend to actually move your arm in that moment. That is happening within your brain. We always talk about how the body and brain are not separate, but a single entity. Well, the cerebellum and the cerebrum also are really not separate collections of structures. They have a common goal and a common purpose, and they operate in an intricate interdependence with information being sent all the way around by way of our neurons as accurately, as efficiently, and even as predictively as it can possibly be. All right, we're going to broaden a little bit now. We're going to get away from the cellular piece and kind of look, what's the 30,000 foot view here? What's a bigger picture? From the standpoint of function. The organization of the inputs and outputs in terms of evolutionary mechanics goes from basic and primary functions like balance, spatial organization, to fine-tuning and modulation of body and limb movements in that medial zone. And again, this is the unupdated version of what the cerebellum does because it's mostly talking about motor. But in this particular case, you have the vermis, the vestibulocerebellum, and the flocculonodular aspects, that lobe down at the very bottom. That's where we get balance. That's where we get posture. That's where we get vestibular functioning, the interface between the different systems that are involved with the proprioception of our inner ear, our eyes, and our body's position that allows us to maintain an upright state, even when challenged and pushed off balance, or when the ground moves a little bit underneath us. The spinocerebellum, on the other hand, that's between the dotted lines within this graphic. That's the vermis, and the paravermis has traditionally been thought of as almost exclusively motor, and that's pretty much been tested out as well by the new information that we have. The cerebrocerebellum is that outside of the dotted lines. And as I'll show you on a graphic a little bit later, it's actually more territory than is represented within this older version here. And that's where primary cognitive and emotional processing, attention, salience, that's where those higher order cognitive abilities are mediated and to some degree automatized and can therefore be run. I know it's not a great example, but in computer terms, you can think of our cerebrum, our left and right hemispheres, as being the programmer that is sending commands that the cerebellum is monitoring and recording and processing and going, oh yeah, if we ever want to do that again, these are the things that we need to do to make that happen. So the cerebellum, in that respect, from a computer term, really becomes the program that is stored in a part of our brain. And that program can then be automatized by repeating it to the point that we don't have to think about it. So if you do something often enough, this is what we know from rehab when we try to teach people physical skills or cognitive skills. If you practice them over and over again, you get better at them. Intentional practice results in improved performance. And part of it has to do with the cerebellum. You do not have to think about walking while you're having a conversation going down the hallway, because that has been over-programmed and over-learned and is being executed by a part of your brain of which you are not conscious. The rest of your brain you can actually explain, but that part of it does not really have conscious awareness. Might talk about that in a minute if we have time. From a functional standpoint, the predictive nature of the cerebellum can be analogous to the predictive circuits integral to many machine processes. I have, and a lot of you probably have, what is called a smart thermostat in your home, which means you can program it from your phone, but it will also learn over time when you want certain things to happen. And it will also learn the environment in which it exists from the standpoint of, well, if I want it to be 70 degrees at 2 p.m., I'm actually going to have to start adjusting the temperature before that in order to get it to that target. Those predictive algorithms get perfected over time in a smart thermostat. Feedback control, input instruction to controller, to controlled object output response. That is a traditional thermostat. You set it to a temperature. The controller then sends that information to the HVAC unit. The HVAC unit outputs a response. And once that response matches what you told it to do, it will stop doing that. It sends a signal to say, you can turn off now. On the other hand, a smart thermostat has what's on the bottom here, a feed forward and feed back. So you have an adaptive mechanism that has the capability of adjusting in order to get the temperature where you want it, when you want it. It'll even learn what time you usually come home by whether or not there's movement in front of the sensors, and then start to adjust things on that basis too. Now, you didn't come in here to learn about HVAC units today, but the reason that I'm talking about it is because this is what the cerebellum does in terms of fine-tuning. And it does this for motor functioning, which we've known about for a long, long, long time, but it also does it for cognition and every aspect of cognition. Attention, salience, being able to identify, target, tracking, all the smoothness necessary for things to be efficient. It is just a little harder to talk about in analogy form how you make more efficient a cognitive process. from that standpoint, actually, there are a couple of researchers that did a really good job, because this is more of a motor analogy here, the trains. But I'll talk about the other in just a second. Just like adjusting the temperature before you want it to hit the mark, if you want to stop a train in a station, you got to put the brakes on before you get to the station. And so being able to stop the train exactly where you want it. You may have not ever noticed this because we don't have just yet mass rail train system in Omaha. It sounds like they're going in that direction, though, from the sound of it. But if you want to stop a train, if you look on the right, there will be markers. If you ever go to a train station or if you ever go to a subway station, look, there will be a marker somewhere down there, usually with a number by it. Because for a train with X number of cars, the operator knows that they need to stop exactly where that mark is outside of the driver's window to be where they need to be in the station. In order to stop right at that spot, before you get there, you have to apply the brakes to slowly come in and meet that point. Let it drift up to it and then lock it down. This is how the cerebellum works. It helps predict if I want to do this and do it like that quickly. My brain has to predict on the basis of proprioception how fast is your arm moving and when do I need to put the brakes on. If you do it really, really fast, you got to stop it in a hurry in the right spot or you're going to flick yourself in the nose. Same thing with the train. If the operator of that train had no way to look out the front windshield whatsoever, could only look out the side window, what they would do when they come to the station is they would drive past it because they, oop, well, there it is, hit the brakes, back up, and then they would do this, and then they would do this and this. That is very, very similar to what happens when you take the cerebellum out of a motor function. It goes from being this to being this. That jerky back and forth motion is motor signals being sent without the moderation of predictive algorithm. So that is very, very important. It's easier, again, to envision motor, but one of the best descriptors I think I've heard from the standpoint of cognitive functioning is it sets the stage. It gets things ready for whatever function is about to occur. And the example that they gave in this particular case is a big arena. Going to have a boxing match one weekend. They're going to have a basketball game on Thursday, and they're going to have a truck pull next Saturday. Everybody come out and watch the tractors, right? So how does that relate to this? It's getting the stage ready. It is the crew that comes in and prepares the arena for what the event is about to be so that when that occurs, everything happens smoothly. If you like Broadway plays, it's the crew, it's the sound crew, it's the stage crew. It's everything that goes into setting the stage so that what is planned to happen can happen efficiently and in a way that runs smoothly. From a neurological perspective, a recent paper in March of this year talks about advanced diffusion MRI technique to precisely map the complex cerebellar fiber organizations. And this is from a standpoint of motor functioning as well as cognitive functioning, how information is getting in and out. Now, this is a motor pathway, but it shows the same process. The cerebral cortex sends information by way of the corticospinal tract to the spinal column with collateral information that gets sent to the cerebellum. So it's both going to our spinal signals that'll send that information out to the muscles. Our upper motor neurons send information to our lower motor neurons, and the muscles move. But some of that information goes to the cerebellum. Ascending information from muscles, joints, and other sensory systems, again, proprioceptive information, is coming from the body up and into the cerebellum. All of that is then being read and compared with intent. What is our motor plan? What is it that we are attempting to do? And that is a feedback loop that then allows for fine regulation of that information. So here we are from a couple of years ago. A statement that it might do something other than motor, but we're not real sure in the moment. Well, now we're a couple of more years past this data, and we're getting a much clearer picture of what's happening. More recent data says that our cerebellum is taking an active role. Now, this information, more recent data, if you look at the citation, is from 2000. I went into psychology because I'm not good at math, but I can tell you that is 25 years ago. Why does it take so long for this to evolve into information that we know? Now, there's a lot of reasons why the cerebellum has not been studied quite as much. The researchers have commented on this very question up to and within the past year. There's a 2024 article that Julie Fies and Catherine Stodley published in the Neurobiology of Language. And they said, this is a direct quote from the article, "We see the cerebellum all the time, but we don't know what to say about it." These same authors pointed out that there remains so much to be learned about the brain as a whole, so it's not surprising that the cerebellum should be any different. I mean, I just put together a presentation a couple of years ago about the glymphatic system, the system of waste clearance in our brain and how that operates primarily only in deep sleep mode. That is relatively new brain information, but it's something about our brain that really has only been researched over the last couple of decades and is only going into human research within the last 5 years. So again, new information about the brain is occurring all the time. So why shouldn't there be a lack of knowledge? One potential explanation is the difficulty of studying the cerebellum. It has fundamentally different architecture than the cortex. So there's that. This architecture allows for different computational capabilities. The cerebral cortex has 6 layers within that gray matter. The cerebellum only has 3 layers. Its principal output is inhibitory rather than excitatory, which again is the vast majority of our cerebral cortex. The inhibitory output primarily comes from the Purkinje cell, a cell that only exists within the cerebellum. It does not exist within the cerebral cortex. And then lastly, the organization of those computational circuits within the cerebrum are typically organized into columns as opposed to the expansive parallel network of that outer layer of the cerebellum. So it's alien in terms of the wealth of established brain knowledge that exists out there. Now, one major limiting factor in studying it, again, is its location. Its location in the skull, its orientation tucked underneath the cerebrum. It makes it easy to overlook and even harder to study. It's less prone to stroke-related focal injury, so it doesn't have all the isolated stroke-related history and literature that is out there. The major methods for modern cognitive neuroscience with neuroimaging, neurophysiology, and lesion studies, again, I'm going to quote directly from a research paper, "The path of least resistance is to simply ignore the cerebellum." Most fMRI studies refer to it as a whole brain analysis, but the studies use acquisition parameters that exclude, that mask the cerebellum, or software packages that mask out the cerebellum by default. So that is difficult if you're not even seeing it to find this information. Also, there have been difficulties with utilizing EEG or MEG or transcranial magnetic stimulation, again, because of its location and orientation. Now, progress is being made on all these fronts, and there have been higher resolution cerebellar atlases that are becoming available, that are now out there, as well as registries of individuals who have isolated cerebellar strokes. So to be able to look at specific individuals and then match that up with what we know from these large population studies. So as more researchers focus on this area of the brain, perhaps our understanding will get a little bit better as well. This is the feedback loop that I showed you before, but in this case, it's a purely cognitive function. Inputs synapses the exact same way, goes back up into the region of the brain that is responsible for that. That polysynaptic signal transmission is one of the reasons it has historically been difficult to study. Monosynaptic, really, really easy. Where does one cell terminate and where does the other cell go? If it is a single handoff, that is a lot easier to study. Researchers have had to come up with new ways of studying How do you trace something if it actually passes through several different connections from where it starts to where it goes to? And what they came up with is actually a way of tagging a virus, which could then pass synaptic transmission and be sent on. So scientists have been getting more creative using transneural tracing techniques across synapses with these viral tagged processes. Further advances by Kelly and Strick in 2003 really defined a good closed loop circuit. And if you'll notice, all of this research that was been done in the mid to late 90s to early 2000s, these are all animal studies. This was not looking at human brains at this point. This area, as you see there, projection to prefrontal area 46. Area 46 within our brain is the area that is called Brodmann's area, number 46 there in green on the frontal lobe. It is very much associated with sustaining attention and working memory. Lesions in this area can also impact judgment and reasoning and relevance of stimuli. So something that is very, very important from a cognitive standpoint is being able to be aware of your environment. So salience to stimuli. It is why you have such a visceral reaction when you look down on a hiking trail and see a snake not too far from you. That visceral reaction is salience of that stimuli now takes precedence over everything else, and your sympathetic nervous system kicks into gear so that you can get away quickly. So it is an important aspect, and again, it directly corresponds to an area of our cerebellar functioning, that automaticity to be able to do that quickly. This German study looked an update to the cerebellum and cognition in 2021. They commented on the fact that the cerebellum demonstrates interconnections with almost all areas of our cerebral cortex. According to the current view of the cerebellum, they stated, based on its ability to detect errors and perform motor and mental processes, including building internal models, these are crucial for optimizing these processes, and they are the basis for cerebellar learning across contexts. The last one's probably the most important statement. Through automation and adaptation, these processes become increasingly stereotyped and efficient, and they require less attention. Something that allows the thinking, programming, conscious part of your brain to focus on whatever you want to, while your automatic part of your brain runs the show. Driving down the highway, going 15 miles without ever being consciously aware of anything you've seen in the last 15 miles because you've been thinking about something else, is an ability that is largely driven by the automaticity aspects of your brain, not by the conscious part. Now, when something unusual suddenly comes out of nowhere, that salience of that stimulus gets your attention, and now you're consciously aware that you're driving. But a lot of times we drive without thinking about it. If you go the same way home from work every day for 5 years, that's why you forget to stop at the store that you intended to stop at on your way home, because the automatic part of your brain was driving your car for you. And these are some more recent studies that are looking at these connections in terms of cognitive. So human mapping studies now have been carried out, comprehensively mapping the cerebellum, looking at group averages of over 1,000 subjects in most of these large subject studies, and now they have cumulative data from these large studies that show that. There is an asymmetry of function within the cerebellum that mirrors that within the cerebrum. You got a bunch of language circuits over here on this side in the left hemisphere. In your right cerebrum, you've got a bunch of language automaticity circuits that correspond. When things light up here, things light up here. So the cerebellum is equally involved with all aspects of anything that happens in the cortex. It also sends it back there. The one exception to that at the moment, and again, it's probably just because it hasn't been found yet, is the processing itself of vision. Now, the motoric aspects of vision, salience, movement of the eyes, everything that's associated with motor Yes, that definitely passes through the cerebellum, but visual processing itself at the moment is not felt to be highly reflected within the cerebellum. Possibly, it's theorized, because so much of the human brain is dedicated to that visual processing. The entire occipital lobe does nothing but visual processing. And so they're thinking that might be the reason, but I'm going to show you another thing here in just a second that brings that finding into question too. A lot of times when we say it doesn't do that, it's because we don't know that it does that yet. So as a scientist, you always have to be able to change your mind when new data comes along. And that's exactly why this presentation looks a whole lot different than one you might have sat through a few years ago in here. I use some of the same graphics because I'm lazy, but this graphic right here, I don't expect you to memorize it and there won't be a test. If you want to get really deep in the weeds, though, this is a table from a study published last year that graphically represents the interconnection of various aspects of the different lobes of the cerebellum with major landmarks, lobes, and structures within the cerebral cortex. As you can see, if there are more colored blocks on a given horizontal line, that reflects a greater number of locations within the cerebellum that are directly connected to that part of the cerebrum. In particular, there is a huge amount of interconnectivity between the frontal lobes. That is the last kind of orange looking, the stripe that's mostly green with a few purple dots in it. That is the part of your brain within your frontal lobes that is, constantly consciously aware of everything that is going on. That's your executive functioning. So you have very dense interconnectivity between the frontal lobes. That superior frontal gyrus that's represented on that line with the most number, the precentral gyrus, which also has a lot of connections, and the paracentral lobule, the thalamus and midbrain structures as well. Now that makes sense because everything coming to and from the cerebellum and the cerebral cortex has to go through the thalamus. The thalamus is the UPS distribution center of the brain. Everything passes through there. So that would make sense that would be the case. But there is just a ton of mapped information now for what goes where. This is the one that I said might make you question what I just said about the occipital lobe not really being that represented within the cerebellum. Well, if that was the case, that's the centermost and the one to the left center. Between the cerebral cortex and between the cerebellar cortex and the occipital cortex, there are a huge number of fibers. And if there are a whole bunch of fibers there, then there's probably a whole bunch of information that's being passed back and forth. So that just shows, regardless of which aspect of our cerebral cortex you look at, it is intricately interconnected with the cerebellum, every piece. Now, this image is from a study that came out last year. This is a Canadian group of researchers in several departments who took multiple large databases and present this cerebellar atlas. These are the locations within the cerebellum where these functions happen. And if you will notice, those that have an M in front of them, those are motor. We used to say that the cerebellum is exclusively responsible for mediation and regulation of motor function. But only about 15% of it has an M tagged on it. So that means the other parts are doing other things. What you're looking at there, motor is individual body movement. So you got somebody in a scanner and you ask them to move a part of their body and it maps where in the cerebellum is that being regulated. The A that you see, that's action. That's activated during action observation. So in other words, you're looking at movement. You are looking at something that is in action. The D's, that is functional demand, multi-demand as well. That would be specific functional domains of the brain associated with higher level cognitive processes. This is working memory, executive functioning, our ability to visualize imagery. These are all things that have no motor component to them whatsoever. And as you'll see, it is a big chunk of the cerebellum, as is the social linguistic. That's activated by tasks involving language and social processing. So what we have traditionally thought of as just being associated with motor movement, most of it is not. So this is going everywhere. Isolated cerebellar damage, again, in rehab, we've known this for years because if somebody has an isolated cerebellar injury or stroke, you can see cognitive or emotional changes, dysregulation, executive functioning difficulties, which are not explained by the neocortex because it was not affected by that injury or by that stroke. And so that has been the proof in the pudding for many years of the fact that that is something that can occur as a result of damage exclusively to the cerebellum. And the part of the brain that is most distal from the cerebellum is the frontal lobe. And it is the part that, from what we can tell now, is one of the more interconnected. It's also one of the largest, from an area standpoint, aspects of our neocortex. And so there's a tremendous amount there of information that is constantly being sent. Now, this connectivity, all this information about non-motor function has resulted in a shift in conceptualization of cerebellar syndrome, which traditionally was just motor dysfunction. In other words, ataxia, for example, or impaired balance or impaired gait or incoordination of voluntary movements. Even dysarthria from a speech standpoint, which was looked at as purely motor. But now this is being recontextualized as a three-part syndrome. So now they're breaking it down by either a cerebellar motor syndrome, a cerebellar vestibular syndrome, or a cerebellar cognitive affective syndrome. That last one, CCAS, is the new addition, the new kid on the block. The cerebellum has a strong role in fear conditioning and emotional learning through connections to our cortical brain regions, and also midbrain structures like the amygdala. That is where a lot of fear conditioning comes from. The interconnections between that and our sympathetic nervous system are also very tightly joined together. The cerebellum is increasingly recognized as playing a significant role in social cognition, helping us learn and understand social action sequences, allowing individuals to predict and anticipate social interactions, and facilitating smooth social behavior through its ability to detect either violations of social norms or adapting to those when they occur. So essentially, it acts as a predictor of social events. If you go into an interaction with a person, you already kind of anticipate how that might go, and you've got probably plan A and plan B in your pocket, depending on what direction that heads. And the cerebellum gets taught that by repetition and repetition and lots more repetition, and it becomes automatic and it flows without you having to think about it. As proposed by Masao Ito, he was an neuroscientist and author who wrote a lot about the cerebellum. Our central nervous system contracts and relaxes muscles to make purposeful movements, and we manipulate that through our mental domain formulistically as a controlled object. And an idea or a concept within the mental domain is analogous to a body limb within the physical domain. From a cognitive and emotional standpoint, we have these constructs that we are aware of and predict will occur and can manipulate from the standpoint of our own output as well. Again, it's difficult to represent because as yet it is a hypothetical construct. Much of what the brain does is not available to our consciousness. Non-declarative memory. Once you know how to ride a bike, you know how to ride a bike. But you don't remember the muscle steps involved. You remember the practice and you remember the repetition, But when you learn a physical task, it's not something that you can repeat exactly when you learned each step in the same way that you can tell somebody when you learned a given fact. That declarative memory is very, very different. Observable physical experience is recallable, but the actual fine motor adjustments and balance and such are not recallable through our processes. Implicit learning from that standpoint of recall is very different from our ability to return declarative. Transcranial magnetic stimulation of the neocortex typically results in a conscious experience. So in other words, if you stimulate an area of the cerebral cortex, that will result in a motion, a feeling, a smell, even visual if it's in the right place. On the other hand, transcranial magnetic stimulation of the cerebellum or the basal ganglia has no impact on our conscious awareness, further illustrating the likelihood that we are not consciously aware of that information once it passes out of our conscious thinking brain. This is what the cerebellum does. It doesn't generate a lot of stuff. It just makes it run smoother, makes it run better, makes it run more automatic and more efficient. BASF had this for years and years, and I thought that was a great motto. All this stuff comes from researchers who have a foot both in computer science and in neuroscience. There was a couple who for many, many years were involved in the development of the IBM Watson program, who were so trying to recreate human thought in a computer that they also went back to school and got trained in neuroscience so that they could make those analogies and figure out exactly how can we make this thing mimic what's going on in our brain. So automaticity is a big part. The things that we can do more efficiently, that gives us the ability to move on and think about other things. And then programming, again, like I said before, that part of the brain that lets this program run automatically, leaving us to consciously think about other stuff. End of the line is we're just learning a lot of this stuff. It's just moved into human studies subject within the last few years. How do we apply this within the rehab world? It doesn't change anything we've done because we've always done repetition. We know that people get better when they practice something. When we set up the structure in order for them to be successful at the earlier steps of what they are working toward and repeat that until it becomes automatic, people get better. Whether you're talking about a cognitive process or you're talking about a physical process. Repetition and practice is what helps. Now we're just starting to kind of learn some of the neurology behind that automaticity. Probably not going to change what we do a whole bunch because what we do is working, right? For the most part. So writing little programs that the cerebellum can operate on. Now, again, like I said, I've got lots of resources here. This is all the stuff that the prior as well as the current presentation are founded on, with a lot of it being very, very recent in nature. 2005 resources, 2004 resources, and a lot of pre-injury stuff. And if you have other questions, I leave it open to the floor now for anybody who might have one. But if you want to dive deep, I would grab a couple of those articles off of PubMed. A lot of these are publicly available because they go through NIH. And for the moment, at least, the NIH is sharing with us. Yes? Question about virtual reality and how that affects. Are you the automaticity of that? Well, I will tell you from my own experiences playing in a virtual world, you get better at defending yourself from knife and gun wielding villains when you play the game more often. And I recently went back to a game I hadn't played in a while, and I started over at the start point several times. Those skills did come back with a little bit. I think the virtual world allows us to practice things that would otherwise be too dangerous or that we're not capable of doing in a way to learn how to do it safely. Virtual driving simulators, for example, are something that we use often to make sure that somebody's going to be safe in the real world before they get out there. So from a learning standpoint, yes, we can learn through that as well. It's better if it is contextually based for that unique individual, for the skill that they're trying to learn. Again, like most things that we know about the brain, when we learn something through repetition, it doesn't tend to generalize to other similar motor skills. Same thing from the standpoint of cognition. So very specific to the task that you're attempting to train. But if it can be represented within a virtual world, yes, absolutely, that gives you more opportunity. If it can be gamified, you're more likely to do it because it's fun or scary, depending on the game. Yes.
Studies out there about professional athletes and have like a higher functioning cerebellum?
Question about athletes and cerebellum. It hasn't gotten to the point where I've seen any studies that are isolated on a specific population beyond those who have experienced some lesioning at this point. But that would be a wonderful study to see, quite frankly. And I would guess that some of the major tier 1 universities who are routinely scanning their athletes could very well compare their findings with those of those cerebellar atlases that currently exist. But oftentimes, this is where we come about as rehab professionals. Oftentimes, if you want to get better at something, you get a coach who really knows a lot about it and knows how to teach it as well. And that's what we are. We're all golf coaches for brain injury and spinal cord injury. Yes.
Cerebral lesions, I'll ask them to do like a long arc quad, or I'll ask them to raise their hand up and they look at me like I've got 3 heads. But then if I ask them to do something like get out of bed, they can do that.
Yep. The question has to do with, does this explain why individuals with the neocortical or cerebral insults are sometimes able to do things that are more automatic in nature? And any of the speech therapists in here want to answer that as well. Melodic intonation therapy, singing changes what people are able to say. People who have very, very dense aphasia after a brain injury, who are not able to intentionally produce a given word even through repetition. If they hit their thumb with a hammer, they will say whatever they would have said when they hit their thumb with a hammer before they had aphasia. Automatic speech. One of my keywords, pass me in the hallway. Jeff, how's it going today? Fine, fine, fine. If I'm aphasic, fine's going to come out just fine. But if I had to say something else, if I consciously had to choose a word, I may not have access to it. I may not be able to do that. So yeah, from a motor standpoint, doing something that you do without thinking about it, including very complex multi-muscular movements, are something that someone can do, even if they can't intentionally generate those movements from the standpoint of their cortical function. Really great question. Yeah.
Forward feedback mechanism and like the overshooting and all of that.
Yeah.
And retraining that repetition and just doing it and making sure it is precise.
Yeah.
But from the cognitive standpoint, how do you retrain that unconscious? Do you make it conscious? Like,
I think in some cases how do you retrain the cognitive aspects? Motor aspects are visible and easily observable, and you can see them. The only difference between what the cerebellum does with cognition and what it does with motor is that that's typically not observable to us. We don't get to see it. You do get to see the improvement over time with changes that occur in recovery or learning to use some augmentative or alternative means of expressing that same function, either from a motor standpoint or from a cognitive standpoint. But the repetition with it is doing the same thing in either case. Yeah. And again, even if that part of the brain that generates that is not working well because of injury or lesioning, the cerebellum has the capability of running that program if it already exists, if it is an overlearned and automatic type of function. I do think that it can also be taught as an overlearned and automatic function, even in the absence of that signal being sent from the brain, because half of the information coming to the cerebellum is coming from the body, not coming from the brain. Any other questions? If not, I thank you all for your attention.
That concludes the online education. I would like to thank all of our presenters for their experience, knowledge, and expertise. Be sure to subscribe so you're up to date with all of Nebraska Methodist College's continuing education offerings. Thank you.